So we have seen the lattice vibrations of monoatomic and diatomic crystals lattices in one dimension. Now we will discuss about the specific heat. So you know what is specific heat? It can be defined as the heat required to raise the temperature of 1 gram molecule of the substance through 1 degree Celsius. That is, it can be represented as C, which is equal to dq by dt, amount of heat required to raise the temperature through 1 degree Celsius, where dq is the amount of heat added to the system to raise the temperature from T to T plus dt. The quantity of heat required to increase the temperature of a body is different under different conditions. Accordingly, one can have various types of specific heats. For example, the specific heat at constant pressure, which is represented by C suffix P, is generally different from the specific heat at constant volume, C suffix V. Cp is always greater than Cv. That is, specific heat at constant pressure is always greater than that at constant volume, because much more heat is required to raise the temperature to the desired through 1 degree Celsius. According to the first law of thermodynamics, the heat added to the system is used by the system in two ways. Firstly, to increase the internal energy of the system, thereby raising its temperature, and secondly, to do some work on the system to increase its volume against an external pressure. So you know all these facts. According to first law of thermodynamics, when we are applying a heat to a system, it is used up in two ways. One is to raise up its internal energy and another is to do work. The latter quantity may have different values under different conditions. That is, the amount of work is different under different conditions. If the system expands against a constant pressure, then the first law can be written as dq is equal to dE plus pdV. Here dE is the change in internal energy of the system and pdV is the work done to change the volume by an amount dV at pressure P. If heat is added to the system at constant volume, then dV will be 0. Constant volume means there is no change in volume, so that dV is equal to 0, and the specific heat at constant volume can be represented using the above equation as Cv is dq by dt at V. Here in this equation dV becomes 0, so dq by dt at constant V means dou E by dou T at constant V. Similarly, one can express the specific heat at constant pressure as Cp, which is equal to dq by dt at P. So in gases, there is a large difference in Cp and Cv. However, in solids, due to a small change in volume, Cp is almost the same as Cv, particularly at low temperatures. For this reason, the term specific heat of solids is commonly used in case of solids. However, it strictly means that the specific heat at constant volume and is given by the above expression of Cv. So the difference of this heat capacity in case of solids and gases are discussing here. That is, in solids, since there is only small change in volume, Cp is almost almost the same as Cv, particularly at low temperature, because there won't be much change in volume, so Cp and Cv almost same. So for this reason, the specific heat of solids is commonly used in case of solids. However, it means that the specific heated constant volume and is given by this expression. Okay. Thus, in solids, most of the heat supplied is used up in increasing the internal energy. Since the volume is almost constant, the supplied heat is almost used up to increase its internal energy. The increase in internal energy of the solid may occur in two ways. The first one is the atoms which ordinarily vibrate freely about their equilibrium positions are set into rigorous vibration. This is manifested by a rise in temperature. So, the increase in internal energy of this solid system can be manifested by two ways. The first one is the rigorous vibration of the atoms, which means the increase in its internal energy. And the second one is the free electrons. In case of metals and semiconductors, get thermally excited to high energy. This is the second one. So the free electrons are and the semiconductors are excited to higher energy states. The first contribution, that is an increase in internal energy and hence vibrations, arises from the atomic vibrations and may be called the lattice specific heat. So the increase in internal energy due to lattice vibration is called lattice specific heat. The second contribution arises from the electronic system, that is the excitation of the free electrons to the higher energy states, and is relatively a small contribution. Thus, in general, the specific heat, the contribution to the specific heat can be occurred due to these two factors, and the specific heat of solids can be expressed as C solid as C lattice plus C electron. That is C lattice means due to lattice vibration, and that this is due to electron excitation. It is assumed that no free electron are present. It is assumed that no free electrons are present, and the specific heat of a crystal is only due to the excitation of thermal vibrations in lattice. That is, only lattice specific heat is to be considered. So occasionally the term heat capacity is used instead of specific heat, and is defined as the heat required to raise the temperature of the complete mass or volume of a solid through 1 degree Celsius. The specific heat is the heat capacity per gram or unit volume. So these two terms are used as usual mutually in this sense. The experimental facts about the heat capacity of some representative inorganic solids are given as follows. That is, the heat capacity of most of the solids at room temperature is close to 3 Nk, where N is the number of atoms in the solid and K is Boltzmann constant. For 1 mole of atoms, the heat capacity is given by 3 Nk, where 3 N suffix A, where Na is the Avogadro's number. Its value is 25 joule per mole Kelvin or 6 calorie per mole Kelvin approximately. So the heat capacity of most of the solids is close to 3 Nk, where N is the number of atoms in the solid, and for 1 mole of atoms this N will be Avogadro number, and its approximate value is given here. And at lower temperatures, that means T tending to 0 Kelvin, the heat capacity decreases sharply and follows T cube law for insulators and T law for metals. If metals become a superconductor, the decrease is even faster. So the heat capacity follows the temperature. That is, at low temperature, heat capacity decreases sharply and follows T cube law for insulators and follows T for metals. And in superconductors, the decrease is even faster. And the third point is in magnetic solids, that is in magnetic materials, the heat capacity increases near the Curie temperature when the magnetic moments become reduced. This is also true for alloys exhibiting order-disorder transformation. So these are similar to alloys which exhibit order-disorder transformation. So we will discuss the theoretical explanation of the facts regarding the lattice heat capacity. This discussion is primarily applicable to insulators. Okay. Now we will discuss the classical theory of lattice heat capacity. Classical theory of lattice heat capacity. A crystal consists of atoms which are arranged in a periodic manner and are bound together by strong binding forces. These facts we know. Each atom is free to vibrate about its equilibrium position and contributes a three-dimensional harmonic oscillator. So, in this arrangement, each atom is free to vibrate about its equilibrium position and contributes or represents a three-dimensional harmonic oscillator. The effect of imparting thermal energy to solid is to increase its internal energy in the form of vibrational energy of this harmonic oscillator. Thus, in the classical theory, it is assumed that each atom of a crystal acts as a three-dimensional harmonic oscillator and all the atoms vibrate independent of one another. So, what happens when a heat is applied to a crystal system? The supplied heat is used to increase the internal energy or vibrational energy of these harmonic oscillators. That is, each atom represents a three-dimensional harmonic oscillator. Okay, and which vibrates independent of each other about its equilibrium position. So, a system of n vibrating atoms or n independent three-dimensional harmonic oscillator is equivalent to a system of 3n identical and independent one-dimensional harmonic oscillator. So, if we have a system of n atoms and each atom represents a three-dimensional harmonic oscillator, which can be equated to a system of 3n identical and independent one-dimensional harmonic oscillator. This is because each vibrating atom has 3 independent vibrational degrees of freedom, and according to the principle of equipartition of energy, the vibrational energy is distributed equally among all the 3 degrees of freedom, so that we can represent the system as one-dimensional 3n identical one-dimensional oscillators. Thus, each vibrational degree of freedom can be regarded as one-dimensional harmonic oscillator. We assume that each harmonic oscillator vibrates with its natural frequency omega 0. However, the energies of these oscillators may be different because they may vibrate with different amplitudes. Our assumptions here is that each harmonic oscillator have a natural frequency, but these oscillators may have the energies of these oscillators may be different because each one may have different amplitudes of vibration. Also, each oscillator may acquire any value of energy varying continuously from 0 to infinity. In order to determine the heat capacity of a solid, we find out the average thermal energy of a single one-dimensional harmonic oscillator and multiply it by 3n and use equations for the heat capacity. So what we are doing is we are considering this 3n one-dimensional harmonic oscillator, and we assume that each acquires a value which may vary from 0 to infinity, and it is used to find out the heat capacity. Okay, so we know the heat capacity as dq by dt. In case of solids, it is the specific heat at constant volume. So it can be represented as dq by dt at constant volume, which is nothing but dou E by dou T at V. The energy E of a one-dimensional harmonic oscillator of mass m and angular frequency omega 0 is given by E is equal to P square by 2m plus V of x. So this is kinetic energy, this is potential energy, and sum of this energy will give you the total energy of this harmonic oscillator. Where P being the momentum and V of x is the potential energy at a displacement x from the mean position. This is the usual terms that we are used in order to represent a harmonic oscillator motion. Assuming that the distribution of oscillators in energy obeys the Maxwell-Boltzmann distribution law, the average energy of each harmonic oscillator is given by, you have studied the different distribution laws in your statistical mechanics classes. So according to Maxwell-Boltzmann distribution law, the average energy of this system can be represented by this expression, integral over E exponential of minus E by kt dE by exponential of minus E by kt dE. Using this expression for energy here, so we have written the energy expression like this. So we are using this expression in this average energy expression, and we are writing this equation like this. So here, instead of P square by 2m plus half Vx, where Vx is m omega 0 square, x is half m omega 0 square, x square, and in the exponential terms also an E factor appears. So we are substituting this E here, P square plus, and we are splitting this exponential term here. So two terms, and here a minus sign also. So minus P square minus this term. Okay, and this is a function of x and p. So the integration with respect to dp and dx. Okay, so the integral is over x and over p, and the denominator is similarly we are substituting for e and 2 exponential term here. Okay, now what we are doing is we are expanding this bracket and separating these terms. So the first term will be in terms of momentum P square by 2m, and this term exponential P square and this term. Okay, first term is this into this into this. So this is first term, and the second term is plus this term into this term into this term, and we will get this term, and the denominator is same. So in this expression, the integration is with respect to x and p. So the first term, in the first term, this can be integrated with respect to x first, so that the integration with respect to p can be kept as such. And similarly, we can apply this rule to the second term also, and we will get the reduced form of this equation like this. The first term will remain with the integration with respect to p only, and the second term with x only. Okay, you can write down in a notebook and detailed step if you want. Okay, and we will get the reduced form like this. Now we are applying the definite integral form, integral 0 to infinity u square exponential of minus a u square du is equal to 1 by 4 square root of pi by a cube, and this 2 and this for numerators and this for denominator, and we are applying this in this equation. This energy, this expression is reduced to this form. You can also apply this integral here by writing down in a rough book. So we'll get this expression, two terms. Here there are two terms, so we will get two terms like this. And by solving these two, this will reduce to half kT plus half kT, which is nothing but kT. Thus the total vibrational energy of a crystal containing n identical atoms or 3n one-dimensional harmonic oscillator becomes E, which is 3Ne, which is equal to 3n into kT. So this is for a single case, and for n case the total hour energy become 3n kT. Here case Boltzmann constant, that is why suffix B written here. The total vibrational energy of the crystal is independent of the type of frequency distribution of oscillators assumed in this model. Also, the energy E depends only on the temperature provided the volume remains constant. So, what is clear from this expression is that the energy is dependent only on temperature. The heat capacity of a solid consisting of n atom is Cv is equal to dou E by dou Tv. So we have got the energy expression. So if you are differentiating this expression with respect to T at constant volume, it will give you the heat capacity, which is nothing but 3n into K. The molar heat capacity is therefore given by CVM. This is for representing molar heat capacity at constant volume, which is 3Na Kb. This is Avogadro number. This is Boltzmann constant. So this is nothing but 3 into R, which is 5.96 calorie mole Kelvin. So this was 6 when we were discussing in the previous section. Thus, according to the classical theory, the molar heat capacity of all the solids is constant and is independent of temperature and frequency. So what is clear from here is that the heat capacity of all solids is constant, because molar heat capacity is 3, here it is 3 Nk, and it is independent of temperature or frequency. This is called the Dulong-Petit's law. This result is in agreement with the observed heat capacity for a number of solids, including metals at high temperatures and often at room temperatures too. The theory, however, fails to account for the value of heat capacity at low temperatures. So, the heat capacity is found to be a constant, independent of frequency or temperature, and it obeys at high and room temperature, but found to be failed at low temperature. This is a graph of this heat capacity. Y-axis showing heat capacity and x-axis is temperature. From this figure it is seen that the heat capacity appears 0 for silver, germanium and silicon as temperature approaches 0. So according to this expression, there is no temperature dependency on there is no dependency on temperature for heat capacity. So but from experimental observation it is clear that it goes to 0 when temperature goes to 0, that is there is a temperature dependency. So that's what we said here, that it fails at very low temperature, that when temperature falls or approaches to 0, it goes to heat capacity goes to 0. So this is a discrepancy from this theoretical prediction. So this discrepancy was solved first by Einstein and then by Debye by using the quantum theory. So this is a classical explanation of heat capacity, and we found that it is failing at low temperature, and this discrepancy is first solved by Einstein, and the remaining discrepancy is solved by Debye. So we'll discuss next about the Einstein theory or Einstein explanation of lattice heat capacity. So Einstein in 1911 attempted to resolve the discrepancies of the classical theory of specific heat by applying the Planck's quantum theory. So this the previous case, the prediction, the discussion was classical, by the application of classical theory, and the Einstein came with a quantum theory. Einstein retained all the assumptions of the classical theory as such, except replacing the classical harmonic oscillator by quantum harmonic oscillator. So what Einstein did was, he kept the classical predictions as such, except the assumption of quantum oscillator instead of classical harmonic oscillator. So the salient features of the Einstein's theory can be listed as follows. A crystal consists of atom which may be regarded as identical and independent harmonic oscillator. So the first one is a crystal having a number of atoms and which may be regarded as identical and independent harmonic oscillators. And the second point is that a solid consisting of n atom is equivalent to 3n one-dimensional harmonic oscillators. Third one is all the oscillators vibrate with the same natural frequency due to identical environment of each. These all features are similar, exactly similar what we are considered in the classical theory that we said before, that Einstein had kept all features of the classical theory except the quantum concept. And the fourth point is the oscillators are quantum oscillators and have discrete energy spectrum rather than a continuous one for classical oscillators. So this is the difference. So Einstein assumed that each oscillators are quantum oscillators instead of classical oscillators. So these will not have a continuous distribution of energy but discrete energy values. And the fifth point is any number of oscillators may be present in same quantum state. And the sixth one is the atomic oscillators form an assembly of atoms which are distinguishable or identifiable due to their location at separate and distinct lattice sites, and hence obey the Maxwell-Boltzmann distribution of energy. Okay, here also it follows Maxwell distribution. Considering the Planck's quantum theory, the discrete energy values of an oscillator with a frequency nu are given by, so according to Einstein, by the quantum concept, the energy of the oscillator can be given by n is equal to nh nu, or by substituting the natural frequency of oscillator, it can be written as nh cross omega 0. This is nh cross omega 0, where n is varying from 0 to n extra. These are quantum numbers. So Einstein later used the wave mechanical result which gives the energy levels of the harmonic oscillator as, so instead of nh cross omega 0 he replaced, or nh nu, he replaced the energy by the wave mechanical result which is n plus half h nu or n plus half h cross omega 0, where half h cross omega 0 is the temperature independent 0 point energy. Energy contribution to the internal energy of the oscillator. We replace this will obtain by n for substituting n for 0. That will give you the energy value half h cross omega 0. This is a 0 point energy. We replace integration by summation in the expression for MB distribution for energy. So we have already said that the energy is discrete in the quantum concept. So we are replacing the integration sign by summation here. So the integration sign is replaced with the summation, and so the average energy expression becomes n is equal to 0 to infinity n exponential of minus n by kt, and the denominator like this. In the previous case this was an integration sign using the MB statistics. Using the previous equation, that is the equation for energy, this expression n plus half h cross omega 0, and we are substituting this here, we will get A is equal to, we will get summation of n is equal to 0 to infinity n plus half h cross omega, and we are substituting for energy expression just as we did in the previous case, and we are splitting the terms like this, and what we are doing in this step is we are substituting for minus h cross omega 0 by kt as x, so that this equation is become n plus half into x. Here this minus this term will become x. And what we are doing here is we are expanding this series by substituting n is equal to 0, 1, 2, 3, etc. and for denominator, and we will get the expression like this, h cross omega into half. This is for n is equal to 0, this is for n equal to 1, n equal to 2, etc. and similarly for denominator. So this can be written as h cross omega 0 into these two terms together can be written as d by dx of ln e to the power x by 2, e to the power 3x by 2, etc. This will give you these two terms. Okay, so in these steps what we have done is we have taken e raised to x by 2 outside the bracket, so the inside the bracket it will become 1 plus e raised to x, e raised to 2x, etc. Now log of, this is natural log of 1 plus e to the power x plus e to the power 2x plus etc. is nothing but minus ln 1 minus e to the power x, and we can write this term as h cross omega 0 d by dx of ln of x, e raised to x by 2 is x by 2 minus ln of 1 minus ex, so, because this term is this, so we will get these steps. And what happens if we differentiate with respect to x, the first term will become 1 by 2 and this term will become e to the power x by 1 minus e to the power x. Now we can write this term as this. This is nothing but this term itself, and x is nothing but minus h cross omega 0 by kt. So minus x will become plus h cross omega 0 by kt, so we will get this expression. So what we have got for average energy is half h cross omega 0 plus h cross omega 0 by exponential of h cross omega 0 by kt minus 1. If we are using the energy expression, this is the average energy expression, and we have substituted for energy this term. If we are using this energy expression instead of n plus half h cross omega 0, if we are using n h cross omega 0 in this expression, we will end up with this expression instead of this, that is half h cross omega 0 will not be there. If you want, you can write down or check by substituting A is equal to nh cross omega 0 in the average energy expression. So we will end up with this equation. Okay, so this equation is identical to equation 60. These two equations are identical except for this term. Just the temperature independent 0 point energy. As for t tends to 0, is equal to average energy equal half h cross omega 0. Thus, according to quantum mechanics, the atoms are not at rest even at 0 Kelvin, and each atom possesses the vibrational energy of half h cross omega 0. That's what is clear here. So this energy, however, has no contribution to CV. This energy has no contribution to heat capacity. It may be noted that the expression for this average energy, this F50, this expression also contains the frequency of the oscillator, in contrast to the corresponding expression of the classical theory. In the classical theory, energy in the total energy was kT. So it is there was no frequency term, but in this expression there is a frequency term coming. The expression for the internal energy of the crystal becomes total energy becomes 3n into E. So we can write the this is the average energy. So the total energy can be written as 3 by 2 n h cross omega, and the second term is this. This we obtain from this equation by multiplying with the 3n. So the heat capacity is nothing but dou E by dou T at constant volume. So we will get heat capacity from this expression by differentiating with the T at constant volume. So the first term will vanish and the second term will remain after a differentiation with the T like this. Okay, so let theta E is h cross omega 0 by k. So what we are doing is we are substituting this h cross omega 0 by k as theta E, which is known as the characteristic temperature or Einstein temperature. This equation can be written to 3nk theta E by T whole to the power square into e raised h cross omega 0 by k as theta E. So we will get this expression. Now we will check the different cases for high temperature behavior. So at high temperature means that is omega 0. Kt very much greater than h cross omega 0 means T is very much greater than, because h cross omega 0 by k is theta. So which means T is very much greater than theta. So we can write this term e to the power h cross omega 0 by kt minus 1 approximately as, so we are expanding this e to the power x form like this by keeping the first order term only, and etc. minus 1, this minus 1. So we'll end up with h cross omega 0 by kt. And now the energy expression will become half h cross omega 0, because the energy expression is this. So we'll end up here with h cross omega 0 only. So this will cancel out each other. So we'll get approximately, so we'll end up with half h cross omega 0 plus kt. But we have seen that according to our condition kt is very much greater than h cross omega 0. So this can be neglected. So the average energy become kt. Thus at high temperature the average vibrational energy is the same as that obtained from the classical. So the classical theory the average energy was kt. So at high temperature according to the energy according to the Einstein's theory was similar as that of classical theory. And also the heat capacity becomes 3nk h cross this expression. This is the expression for heat capacity from Einstein's theory, and this will reduce to this form. Okay, so we'll end up with 3nk into 1 plus h cross omega 0 by kt. For large t, h cross omega 0 by kt tending to 0, so this term can be neglected. So we'll get Cv is equal to 3nk, which is nothing but 3 into r, for n is equal to Na. That is for 1 mole of substance, which is Dulong-Petit's law, just as we obtained from classical theory. So at high temperatures, this Einstein theory is exactly similar to or exactly coincides with that of the predictions from classical theory of heat capacity. And what happens at low temperature? At low temperature, the condition can be taken as Kt is very much less than H cross omega 0, or T is very much less than theta I. So we can write this expression as, since Kt is very much less than H cross omega 0, this term is very much higher because this is coming in the denominator. So this minus 1 can be omitted. So we will end up with this term. So the average energy becomes half H cross omega 0 plus H cross omega 0, and the remaining term is, this will be exponential of H cross omega 0 by Kt alone. So this can be taken to the numerator, so that we will end up with H cross omega 0 into e to the power minus H cross omega 0 by Kt. It shows that at low temperature, the average vibrational energy decreases exponentially with decreasing temperature. From this expression, it is clear that the average energy decreases with the temperature, because it's in denominator, so this factor is high and there is a minus sign here, so this is exponentially decreases with the temperature. And the expression for Cv, hence the heat capacity equation become 3nk H cross omega 0 by Kt whole square, and the last term will become this only according to this condition. So this term only, or in terms of theta e, we can write this expression as theta e by t whole square and e to the power minus theta e by t. So from this expression, we can clear that for t very much less than theta e, the heat capacity is proportional to e to the power minus theta e by t, which is the dominating factor. Because t is very much less than means this quantity is very high. However, experimentally is found to vary as T cube for most of the solids. But at low temperature, it is found that this variation of his heat capacity follows a T cube law instead of this exponential factor. A theoretical plot of Cv versus T by theta E is shown here in this graph. This is Cv, this is C suffix V, and this is T by theta E. For diamond, this is for the case of diamond at 1320 Kelvin. Some experimental points are also shown for comparison. So this is a curve, and some points are also, some dots are point here. These points are away from this line. It is seen that the Einstein curve fits the experimental points well over wide range of temperature, except for very low temperature, that is at liquid helium temperature. It is shown in the graph, where it falls more rapidly than the observed decrease in Cv, which follows T cube law. So at low temperature, the Cv found to fall very fastly, which following a T cube law instead of this exponential law. Einstein temperature defined by the expression H cross omega 0 by T, which distinguishes between the low and high temperatures, can be determined if omega 0 is known. So this can be determined if we can determine the value of omega 0, or natural frequency of vibration. And this can be determined from the atomic mass and the observed elastic constants of the crystal. And for monoatomic crystal, it is equal to square root of 4 beta by m. So for monoatomic crystal, this natural frequency is given by square root of 4 beta by m. For typical metallic elements, the value of theta E varies from 100 to 200 Kelvin. Although Einstein's model provides a much better explanation for the variation of heat capacity with the temperature than the classical theory, it fails to account for the values of specific heat at very low temperature. The discrepancy arises due to the oversimplified assumption of the Einstein model, in which the atomic oscillators are considered to vibrate independently at same frequency. These oscillators in fact are coupled together, and there may be a number of possible vibrational frequencies rather than a single frequency omega 0. This fact is accounted for in the Debye's model. So in the classical theory, there was no temperature dependence at all for the heat capacity. It was a constant, and by Einstein's theory, by including the quantum theory for harmonic oscillator, the prediction was improved much better, because it at least showed some dependency on temperature, though it's in the exponential form. In actually, the dependency of heat capacity on temperature was T cube low, but the Einstein prediction showed some dependency on temperature, but the classical theory was showing no temperature dependence at all. So the Einstein theory have shown a better explanation for heat capacity. So the discrepancy in the Einstein theory came because of the oversimplification fact that all oscillators are oscillating independently with same frequency. Actually, these oscillators are coupled together, and there may be a number of possible vibrational frequencies rather than a simple frequency. And this fact is considered by Debye in his model of heat capacity, and that will remove this discrepancy completely. So we will explain this in the Debye model of lattice heat capacity. Okay.